Okay, we're going to put fuzzy on the back shelf for a while. I'm going to start to talk about neural networks. Before we start about neural networks, I'm going to give you a little bit of historical background on neural networks and the way that neural networks work and what they're trying to do in terms of classification and regression, because the historical aspects are relatively important. The way I decided to do this is to give a presentation of something called the Fisher discriminant. The Fisher discriminant being a technique which was actually used in 1936 initially, and it's still, oh, the television isn't on. Okay. We'll wait for the television to come on. There we go. Okay, good. Fisher was a really great intellect in the area of pattern recognition and other areas. As we'll discover, he has a number of things in statistics named after him, including the Fisher information, for example, of a distribution. And one of his big contributions was the concept of the Fisher discriminant. Here's the question before us. And this was a question before Fisher. We have data in a very, very high dimensional space. Now, as we mentioned in the beginning, usually we can characterize this data in terms of a feature space. So we have some sort of feature space. And let me do this just in 2 dimensions. We have a feature space, and let's suppose that we have the same feature space that we had before, which is the weight and the height of some people, and we wanted to perform a classification, or if you will, a discrimination between 2 types of people. Let's say jockeys and basketball players. So we would have the jockeys down here, and we would have the basketball players up here. Now, the nice thing about 2 dimensions is that we can visualize it. However, once we get above 3 and 4 dimensions, we can't perform a visualization. There's a classic book by George Gamow called 1, 2, 3 Infinity. He talks about a very primitive tribe called the Hottentots, which had the inability to count above the number 3. They would go 1, 2, 3, and then anything above 3 was beyond their comprehension, and anything was above 3 was referred to as many. And we think that we're so smarter than the Hottentots until we realize that we are somewhat grounded in the same way, because 3 is the dimensions that we can visualize. We can go, yeah, 1-dimensional line, 2 dimensions, yeah, plane. 3 dimensions, yeah, space. 4 dimensions we can't visualize. So we're limited something like the Hottentots. So I'm going to present things in 2 dimensions since we can visualize them, but recognize that what we're going to do is we are going to extend this into higher dimensions, these concepts into higher dimensions. The concept that Fisher had was as follows. He was going to look at that line in which the projection of this data down into 1 dimension had the maximum separability. We want the maximum separability. Let me show you what I mean. I'll first of all show you a dumb line. This is a bad line, because if we were to project all of the data down onto this single line, we would have the zeros here, and we would have the x's right across from each other, right? So this would be a bad line for us to choose in order to project this down to 1 dimension and see a difference between the x's and zeros. What would be a better line? A better line would clearly be this line, because if we projected everything onto this line, by projection I mean finding the orthogonal line down. If we chose this line, I think you can see that along this line that we would have the x's and o's pretty well separated, correct? And once we had everything in 2 dimensions down to this 1-dimensional line, we could put a little threshold in 1 dimension here, and we would say everything on one side of the line was basketball players, everything on the other side of the line were jockey players. Now, this concept extends to 2, 3, 4, 5, 6 dimensions. Even in 6 dimensions, we can project down to a single line. In 3 dimensions, for example, we would project to a plane, and then on that plane we would project on some sort of line. The question that Fisher asked is, if I have some data here, shouldn't there be something in the data that tells me which of these lines that I can choose in order to best discriminate between the 2 classes? And hence we come up with the idea of the Fisher discriminant function. Now, the Fisher discriminant function is actually categorized by a vector, which we will refer to as the Fisher vector. Suppose that we were in the space, and here's our space, here's our feature 1 and feature 2. Basically, what we want to do is we want to find a one-dimensional vector, because for the Fisher discriminant, we are projecting everything down to a single line. Hence, a single line means we're down in 1 dimension, so we're going to have this Fisher discriminant in 1 dimension. So this is a one-dimensional vector in a higher dimensional space, 2, 7, 8, whatever dimensions we have. And we want to find the single Fisher discriminant vector. The nice thing about this vector is as follows. This unit vector, it's a unit vector in the sense that the magnitude of W is equal to 1. Do we all know what I mean by this notation? The sum of the squares is equal to 1, just like in electromagnetics, except it extends to even higher dimensions. So it's a unit vector, so the magnitude of it is equal to 1. And it defines, if you will, a new axis, and we'll call this new axis Y. If we have an arbitrary point outside of Y, some sort of feature space here, like the height and the weight of the basketball player, we can call this X naught, and we will be using vectors. This corresponds to x10 and x20, a vector which corresponds to the height weight of this particular person. Now, what we would like to do is we would like to perform a projection of this X naught into a one-dimensional entity which we call Y naught. And it's much like we have a 2-dimensional space corresponding to X1 and X2, or in general a 3 or 7 or 10-dimensional space, and we have a 1-dimensional space. And the projection between the higher dimensional space and the 1-dimensional space is dictated by this vector W. The nice thing about using a unit vector W, which we'll refer to as the Fisher vector, is that Y naught, which is a scalar, Y naught is simply a scalar here, is equal to the transpose of W. It's the inner product of W with the actual vector. So, and this is generally true. If you would like to project a vector onto another vector, which is a unit vector, then the scalar on this new axis here, which we'll call the y-axis, is simply equal to the inner product of the two. So this would be equal to, let me write these down in a few places. This is the summation of n is equal to 1 to d, wherever d is the dimension of w sub n squared, and then we would take the square root of it. So that would be the Euclidean distance in the higher dimensional space. The inner product here, which is nicely expressed in this vector notation, is equal to the summation of n is equal to 0 to d, d being the dimension again of w sub n times x sub 0 of n. So it's the nth component of whatever x sub 0 is. You'll notice that y sub 0 is nothing more than a weighted sum. It's kind of like an average, because all of these w's, the summation of the squares of them, if you take the square root, add up to 1, and so it has the flavor of a weighted sum of sorts. So this is the geometry that we'll be using. Oh, it should be 1. Thank you. Yeah, it should be 1. Maybe I should do this. X sub 0. In other words, the component of the vector, the nth component of x0 is what I meant. But yes, the lower limit should be is equal to n is equal to 1. Is that okay? Who asked that? Okay, is that correct? Okay. Yeah, thank you. I've been doing too much DSP. Well, let's talk about a few of the attributes of performing the projections in higher dimensions down into one dimension. Let's consider, first of all, the center of mass. That's kind of an interesting one. We have a center of mass corresponding to our jockeys and our basketball players. By the way, if we had more information about the basketball players and the jockeys, would that help us at all? Maybe. How about if we had their age? Don't jockeys ride horses longer than basketball players dribble? I don't know. Okay, but maybe the point is that we're stuck with two features. We're not stuck with two features. We're just using it for illustrative purposes. We could actually enhance that a little bit. So here what we have is we have two classes. We have class 1 and we have class 2. And we would like to compute the center of mass of these classes. In other words, if these were points, where is the center of mass of these? That's simply the equal to the sample mean. So for this class, the mean is equal to the sample mean, or the average, is equal to 1 over n1 times the summation of x's within this class, which we're going to call chi sub 1 of x. So this class 1, what we just referred to as chi 1. Chi for class, kind of words. So the sample mean is just equal to the summation of those. N1 is the number of points within the class. So by doing this, we will come up with a single vector, which is right here, which is the average of all of these vectors, which is the center of mass for this class, which we're going to call M sub 1, corresponding to the sample mean of the first class. In a similar sort of fashion, we can come up here to class 2, chi 2, and we will perform the summation here. Notice there's really nothing that says that the number of jockeys and the number of basketball players have to be the same. And we will come up with some mean here, some vector mean, which we will call M2, and that will be the center of mass of that class. Now what I'd like to do, if we're given a W, remember what this W is, this Fisher vector. This vector allows us to project down into a single dimension. If we are given this single value of W, we might ask ourselves, what happens when we project the mean to this point? So in other words, we choose a W. I was told I'm only allowed to use black. So what do I do now? I draw more black, right? What? Oh, dash lines. Okay, dash lines. Okay. See how clear that stands out? Okay, so this is my W now. This is my Fisher vector. I continue out with my Fisher vector now. And what I'd like to do is I would like to project this mean onto this space. I would like to project this on to this space. And I'm going to call this M2, I think M2 twiddle. Yeah, M2 twiddle. I'm going to call this M1 twiddle. So you get the idea of what I'm doing? I'm taking just the center of masses and I'm projecting those center of masses corresponding to the Fisher vector. Well, the M1 twiddle is going to be equal to the unit vector times M1 with a transpose. So that's the projection there. And then the M2 is equal to W transpose times M2. Now here, what we're going to show is kind of interesting. We're going to show the following. If we project all of these zeros on here, there will be a center of mass in the one-dimensional sense, right? There'll be a center of mass in the one-dimensional sense. Is that center of mass in the one-dimensional sense equal to the projection of the two-dimensional mass onto the one-dimensional mass. Do you understand the question? We have two processes. Number one is project the points and find the mean in 1D, right? The second one is project the 2D mean into one dimension. So these are the two propositions that I'm giving you. So first of all, we project the points. We would project all of the points of the jockeys here and then compute the mean along this line, the center of mass along this line. Option number two is we project the two-dimensional mean that we actually computed and we get a point. Here, are those points going to be identical to each other? And the answer is yes, they are. They're the same points. So that center of mass, if you will, is kind of conserved. We can show that pretty easily by remembering that M1 twiddle, or tilde I should say, not twiddle, is equal to this. And what is M1 equal to? That's equal to 1 over, what did I use? N1? Where did I use the mass? Yeah, 1 over N1 times the summation of x within chi1 of x. But notice, all I've done here is I've taken the m and I've replaced it by this relationship, right, which is the definition for the mean. And this, of course, is equal to 1 over n times the summation of x within chi1 of w transpose times x. What is this? What is this a summation over? This is the summation over all of the projections, right? This is the summation of all the projections. This is the same as 1 over n1 times the summation of, say, y within, I give it another name here, y1, of just the y's. So on the top here is we have the projection of the mean. Because we've performed a projection of the mean. Now, down here, what do we have? We have the mean of the projections. So the projection of the mean is the same as the mean of the projections. Doesn't matter which order you do it. You can compute the mean up here and you can project it, or you can do all your projections and then compute the one-dimensional mean. Either way, you get exactly the same result. So this is what we're talking about. Let me draw another black and white picture here. We have a W here. So here's our origin here. We have a bunch of points here. We can, first of all, compute the center of mass, which is M, and we can project this to get the center of mass here, which is M tilde. That is equivalent to taking each one of these and performing a projection. Each one of these performing a projection. I'm trying to draw the same constellation of points here. Taking each one of these, performing the projection here, and then once we have this projection, perform the mean operation in this one dimension, and we will get this, and the result of these two is exactly the same. So this is what I call the projection of the mean, right? The projection of the mean of all the points, and this is the mean of all the projections, and they're equal to each other is what we saw. There's another concept which we would like to have in terms of the projection with a specific class, is we would like to know how far these points are spread out in some sense. And if you have a one-dimensional distribution of points, what is the definition of, what's a commonly used definition for how much they're spread out? Well, it's the standard deviation, right? Or the variance. So another aspect we can use, another measure that we could use once we have projected it in the projection domain, is we can talk, for example, about sigma 2 squared is equal to 1 over n2 times the summation of y within y2 of y minus m2 tilde squared. This is the definition of the variance that's commonly used in statistics, right? If you have a bunch of data. So therefore, if we project these down, now notice this is over the one-dimensional function of y, so therefore I've already performed the projection. I don't have as nice result as the variance of the projection of the variance is the variance of the projection. It kind of becomes nebulous, and it's nonlinear too, so it's not a lot of fun. By the way, some people use what here instead of n2? Anybody know? In fact, on most of the n2 minus 1, instead of the n2 here, use n2 minus 1. It's a commonly used variation. Turns out with the variance, it's not clean always to use n2. It's cleaner to use n2 minus 1 for reasons we won't get into, but you can see that asymptotically they're the same if you have a big value of n2. So anyway, this is the variance in the projection. And we would have a situation like this. If we had our projections like this, 4 points, we would have a small sigma 2 here if the projections were kind of lumped together. Whereas if the points were more spread out, we would have a bigger sigma 2 here. So this corresponds to a small value of sigma 2. This corresponds to a big value of sigma 2. Sigma 2 is actually a measure, if you will, of the variance or the dispersion of the points, and turns out to be actually independent of where it's centered. And I think you can see, at least in the English meaning of the words, that where that thing is centered, those projections are centered, and how far they're spread apart are kind of independent concepts. And indeed they are. So if we have 2 points, these basketball players and jockeys, where we have the height, what do we say, the height, the weight, and the age. Okay, we're putting 3 dimensions. We need one more to put on 4 dimensions. What would one be that would be useful? Salary. Salary. Ooh, good one. Excellent. Okay, so we have 4 now. Height, weight, age, and salary. Okay, good discrimination. So now we're in 4 dimensions, and we're projecting down into 1 dimension, so we can't visualize the 4-dimensional data, which makes it a little bit nicer. Okay, so now what we've done is we have chosen a value of W. This is a 4-dimensional vector, right? And it's arbitrary now. We don't know which one we're going to choose, but if you choose one, I can project down into this 1-dimensional data. And what I will do is I will have the following case. I will have points here in 1-dimensional data, and I will have points here. And what I have done is I have eliminated the detailed information about these points and kind of replaced them with 2 quantities. I've replaced them with the mean. That's the mean of this class and the mean of this class. And I also have now the standard deviation, or how much these are spread, which is sigma 1 and sigma 2. Now with this, we have a different relationship for every value of W we choose. Every 4-dimensional value of W we choose is going to give us a different distribution of sigma 1, sigma 2, M1, and M2. The question that we have is we want to optimize W in some sense. We'd like to optimize it in some sense. What do we want to maximize or minimize? Well, according to Fisher, basically what we would like to minimize is something. This isn't exactly Fisher, but we would like to maximize M1 minus M2. Well, that makes sense because we would like to maximize the separation of those 2, right? But we also need to take into account these sigma 1s and sigma 2s. And also, we want to maximize this, so we got to be careful not to have a sign, S-I-G-N, in here. So let's take the magnitude of this squared. And divide it by sigma 1 squared plus sigma 2 squared. And this is very, very close to the Fisher distance. So he wanted to find the W that performed a maximization of this. And if you look at it, it makes a lot of sense. Because we could have a number of different scenarios. We could have sigma 1 and sigma 2 being very big, which would make this small. Well, sigma 1 and sigma 2, even though you had the means separated out, your sigma 1 and sigma 2 being big could be a situation like this, where there would be a lot of overlap and a lot of ambiguity, even though your means were very, very farly separated from each other. Conversely, you could have very, very close means, but if your standard deviations were very small, then you would have a good ability to perform discrimination. So this is a nice compromise of putting things together. Now, Fisher didn't use this, though. He used something very, very similar, and this is what is referred to as the Fisher distance. I want to use J for the Fisher distance because J is a commonly used variable, commonly used letter in optimization, where you want to maximize an objective function. This is J. This is actually what it is. He said, okay, let's keep the numerator the same, but in the denominator we're going to put something different. We're going to put S1 squared plus S2 squared where the S1s and the S2s were actually the sigmas, but they took into account the cardinality of the data. Specifically, S1 squared is, let's see. There it is. Okay. S1 squared is equal to N1 times sigma 1 squared. And S2 squared is equal to N2 times sigma 2 squared. So in other words, it's just the summation of the squares without the normalization by the N1 and N2. So it has a similar flavor of the standard deviation, but the Fisher distance turns out to be very tractable and also keeps the same flavor of separation, because clearly as sigma 1 and sigma 2 grow, S1 and S2 will also grow proportionately. So the problem is to find the value of W that maximizes this. So we want to find the maximum of J of W. Now you notice that W doesn't explicitly appear here, does it? W doesn't explicitly appear here. However, your projections of the means are going to be a function of W, right? You choose a different value of W, your projections of the mean are going to be different. In a similar fashion, your scatter values here, we'll see why they're called scatter values in a second. These scatter values, which is the dispersion of each of the groups, is also going to be a function of W. So each of these variables is implicitly a function of W. Fisher was able to show, and we will duplicate his result, the following is the vector that maximizes that separation. I have to define one of those terms yet, but this is the result that we have. I need to say first of all that W here is unnormalized, so let's call it W sub f, and then W. How do you normalize a vector? You take the vector and divide it by its norm, right? So this vector in general will not be a unit vector, but it turns out this vector that we have derived points in the proper direction of W. Now, we know what all of these mean. We've defined all of these. M1 is the n-dimensional center of mass for class 1, for the jockeys. M2 is the center of mass for all the basketball players, the center of mass for all of those. The thing we have not defined is SW. Let me define S sub W for you. SW is S1 plus S2. Well, we're still not done yet. S1 and S2 are the matrices which come from the outer products of the data. S1, by the way, I will denote matrices in this class by an underline. I should mention that. In other words, normally matrices are denoted by capital letters. I don't have that luxury, so I'll just put underlines under them corresponding to a matrix. Vectors are easy. You put the little arrow above, but the matrices are a little bit more strange. So S sub W is a matrix, and this is an inversion of a matrix. Okay? So S1 is equal to the following. And there's a similar definition for S2. Yeah.
Does this correspond to maximizing J of W or the original? Is this the Fisher distance or is this the other?
No, W sub F is the vector that maximizes this.
Fisher distance or the other one?
Oh, no, it maximizes the Fisher distance. I'm sorry, yes. The Fisher distance is maximized. The Fisher distance is maximized on this. Right up to here was pedagogical and allows us to kind of a jump between this, which makes a lot of sense to me, and this, which is somewhat more vague. But the idea is that the S1 and the S2 also measure the dispersion, right? And by the way, if your cardinality is the same, if N1 and N2 are equal to each other, then this is equal to this, isn't it? So if you have represented the same exact representation in both classes, they become equal to each other in the sense that maximizing one maximizes the other one. Okay, these are referred to, well, first of all, let's talk about these a little bit. This is the center of mass, the means, the sample means of the jockeys. And notice we're summing not the inner product, but the outer product. When you multiply two vectors together, you can either get a scalar or you get a matrix. Well, this is the way where you multiply two vectors together to get a matrix. And so we're adding up a bunch of outer products. Each one of these turns out to be a D by D, where D is the dimension, matrix. And we're adding up a number of them. It's very akin to the, if you're in statistics, a correlation matrix. Very, 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 very close to that concept. The S1 and S2 are referred to as scatter matrices. And contain the information concerning the dispersion of the results, the dispersion of the data, if you will, in high dimension. So this is kind of interesting because this Fisher distance allows us to do what? It allows us to look at data in two classes in higher dimensions, 100 dimensions, 50 dimensions, whatever. And we know in that, say we're in 50 dimensions, we have a 50-dimensional unit vector that we can put any way we want to. Once we define where we're going to point that vector, we get that vector, that 50-dimensional vector going up there. It's a one-dimensional vector, so it's a one-dimensional line in a 50-dimensional space. And all of the points in that 50-dimensional space are projected onto this line. And what the Fisher distance does, once it's minimized, is that it maximizes the separation between the two classes as defined by the J function. So it maximizes the separation of the means and also attempts to minimize the S1 and the S2. Now, there are different ways where you could, or there are different values of J which you could use to say that we really have good discrimination. Yeah, there's other ones that could be used also. You could have used the median, right, instead of the mean. You could have used the range instead of the standard deviation. However, the nice thing about the Fisher discriminant function is that it's very tractable in terms of the math, as most quadratic things are. So I'm toying with the idea of proving this. I don't think I'm going to. It's 4 pages of really good stuff, though. What I'll do is I will, and I'm sure, when I was a student, one of the most boring things was to listen to long proofs, you know. So I don't want to do that. So I tell you what I'm going to do. I'm going to put it on the web, unless you'd rather me do it. And I'm going to ask you a homework question about it, so you can go in and make sure that you look at it. Would that be okay? Would you prefer that, or would you rather me go through the proof? You're going to know it one way or the other. I'll give you the homework either way, so I guess I know the answer to that. Okay. Well, some of you might like to be elucidated. No. Okay. So let's summarize the Fisher distance. In fact, I have a summary. This is on one of the sheets that I made available to you in a GIF file. So if we could zoom in on this here. Okay, thank you. Can you read that? Kinda. Okay. The first thing is to define the Fisher vector. What you want to do is you want to perform a maximization of this objective function, which is the difference between M1 and M2 divided by the scatter distances. And the solution is the Fisher vector. This is what Fisher showed way back in 1936. Okay? There's smart people back then, too. Where S sub W was something which we call a within-class scatter matrix. Within class because this contains the scatter of jockeys with respect to jockeys. And this does basketball players with basketball players. And we would have without class or cross-class scattering if we did the sum of products of basketball players and jockeys. Okay? Much like a cross correlation. Very, very similar. And the S1s are determined by the math that we show, the sum of the outer products of both classes, and the M's, of course, are equal to the centers of mass of the data in the high-dimensional space. So that is the solution of the Fisher discriminant function. We have left out a big gap between this as the question and this is the answer, and that's the proof that I won't be giving you. It's a 2-page proof and is relatively straightforward. We're going to look at some assumptions that this indeed happens. Let's do some commentary on this. And that a pretty neat result. And in fact, it's still used in pattern recognition today. I just read a paper where they used the Fisher discriminant for, believe it or not, a simple thresholding operation. Wherein one had to decide in a black and white, a gray level image, where to put the threshold. And the threshold was determined by looking at the Fisher distance and choosing the threshold, which maximized the Fisher distance. Because when you choose a threshold, you got your black guys, you got your white guys, and you have a Fisher distance. And by choosing the Fisher discriminant, one is able to do that. I also know in certain industrial applications that the Fisher discriminant is still used. The question is it the best technique? And this is a question which we might ask quite a bit. Is it the best technique? Depends on what you're doing, right? If it works, hey, it's a good technique, right? And it's very data dependent. Typically, before you go into a classification problem, you as an engineer will have specifications on performance. You have a specification on performance, you need a certain number, a certain degree of classification. You have a certain degree of false alarms that you can live with. And usually these specifications are given on the outset. Well, in trying all of these different models, you come up with one that works. And especially if you're in a bottom line startup, you don't care about doing everything and getting the best result, right? You want something that works and gets you within the specification. So these are just different models for doing the same thing. There are some assumptions here. One of which is that SW is not singular. Because the Fisher distance, if you notice here, is equal to the inversion of this result. And the S sub W can actually be written as the summation over all x. This is x in both of the, well, no, I guess you can't do it that way. Never mind. X in chi1 of x sub 1 minus m1 and S sub 2. No, don't yawn. Don't do that. It hurts my feelings. Let me ask you this before we get into the this assumption. Suppose I gave you a four-dimensional vector and I took the outer product of this four-dimensional vector to give me a 4x4 matrix, right? Will this matrix be singular? Yes. It will be singular. In fact, if you know about eigenvalues and eigenvectors, if you take a vector times its transpose, it will have one non-zero eigenvalue and all of the other ones will be zero. It will be a singular matrix. You have to have at least one of these outer products for each non-zero eigenvalue. If I gave you this, would this be singular? If I were in a four-dimensional space, or in fact if I were in a three-dimensional or higher space, this would also be singular. In other words, in a d-dimensional space, in d dimensions, it is required, it is necessary, it isn't sufficient, it's necessary that when I perform these summations that I at least sum over d of them in order to generate a matrix which is non-singular. Each of the outer product kind of takes care of one of the degrees of freedom. And I at least have to have d of them to fill out all of the degrees of freedom of the matrix before it becomes non-singular. Now it could be that some of those vectors in the components might be linearly dependent, so maybe d isn't enough. Maybe coincidentally I got two that were a linear combination of the other one, right? In which case d wouldn't be enough. So there at least needs to be d of them, which means that in order to apply the Fisher discriminant function in a space with 100 points, a space with 100 dimensions, you at least need 100 points, right? You at least need 100 points. You at least need a point per dimension. That's not asking a lot, by the way, right? If your data is in some way correlated, wherein one feature is highly correlated with the other, you'll need more than that, because correlation kind of means, if you will, a dependence. And that dependence being linear might screw this up. So SW must be not singular. And the second thing is that SW, this is a more general condition, must not be ill-conditioned. The condition of a matrix is defined as its maximum eigenvalue over its minimum eigenvalue, and tells us the precision that is needed to compute with this matrix. If you have a singular matrix, the minimum eigenvalue is always 0, so the condition is infinite, right? The point that we're making here is that if this doesn't work when it's ill-conditioned, it shouldn't work when it's, if it doesn't work when it's singular, if this Fisher discriminant doesn't work when it's singular, it shouldn't work when it's ill-conditioned. So if 1 over 0 doesn't work, then 1 over 10 to the minus 50th shouldn't work, because 10 to the minus 50 is pretty close to 0, right? The problem with ill-conditioned matrices is the condition tells us the precision of the math that one has to use in order to manipulate those matrices. And if you use something less than the precision of the math, you're going to get just gross errors. This is not only for the Fisher discriminant, but for any time one inverts matrices. And what the tendency is, if you have a condition number of, say, 10 to the 20th or something, that means you have to use 20 decimals of precision, probably more than that, in order to maintain accuracy in your computations. Otherwise, you have a matrix which is ill-conditioned, which just a little bit of perturbation on the input will amplify enormously on the output. So your system becomes incredibly corrupt to noise, including round-off error and other things. So therefore, we're assuming that S sub W is not ill-conditioned. There's a MATLAB command you can use for that. Is it COND? COND. If you put a matrix in, a square matrix, COND of A, it'll tell you the condition of the matrix. So these are requirements that we must have in order for the Fisher discriminant to work. Yes? We'll get to singular value decomposition later. And yes, you can. The answer is yes, you can. If you can determine, for example, that all of the data lies on a plane, yeah, you would want to go to that plane and do your Fisher discriminant from that plane. Yes. If you didn't understand what that meant, don't worry about it. Now, the Fisher discriminant actually doesn't tell us how to use this in terms of classification. We have rather a technique to take all of this data and to put it on a line in such a fashion that the classes are in some way spread out. That some way being defined by the way we define the objective function. Again, it's not the only objective function that we could use to spread things out, but the math turned out to be really, really easy, and derivatives go really nice, and all sorts of things. So it does work out very nice. Now, once we have this, what do we do with it? Once we perform this operation, what do we do to make it a classifier? One of the ways is to simply set a threshold. After we find W, we have a one-dimensional line on which all of our data is projected. So here are the jockeys, and here are the basketball players. Does it guarantee that they will be totally separated? Absolutely not. And in fact, in many data sort of situations, they won't be separated. But one of the things you'll find out, if there's a lot of ambiguity, if there's a lot of area in here where there's slop, that might tell you, I don't know enough to distinguish between these two different places. You might have, what would be one? Rugby players and soccer players, okay? You would have to have a lot of very defining features in those because the sports are kind of similar in terms of salary? I don't know. But the point is, if you did rugby players and soccer players, you would have X's and zeros shuffled here throughout, right? So you can tell by interactive data involvement, which is always a good way to do things, you can tell by looking at this Fisher discriminant whether it did a good job or not. Because if all of your zeros are on one side and all your X's are on the other side with a few ambiguities in between, you're doing okay. Maybe you got the world's tallest jockey here, okay? Or the, who's that short guy that plays basketball? Who? Spud Webb. Okay. What? Muggsy. He was the one that was on that Bugs Bunny movie. Space Jam. That's right. Yeah, Muggsy was on that. He had his basketball powers taken from him. Very pathetic. So yeah, this is Muggsy, and this is, I don't know, some tall jockey somewhere. So you are going to have ambiguities, and that's life. Now, what are you going to do in order to make this a classifier? Typically, to make something into a classifier after you've performed discrimination is to apply a threshold. And you say anything above that threshold is a basketball player, anything below it is going to be a jockey. And so you can choose the threshold anywhere around here that you want. And I don't know, where would you put the threshold? Right here. That'd be a good place for a threshold, right? Now this turns out to be a case where we have a multi-objective function that we're trying to optimize in terms of the result. Because there's two things that we want to do. Let's put it in terms of detection. Suppose we're trying to detect basketball players. We're trying to detect basketball players. There's two things we want to do is, first of all, we want to make sure that the probability that if we choose a basketball player, given that it's a basketball player, this is conditional probability, this is our detection probability, which we'll call beta. We want to make that as big as possible. Given that the probability, wait a minute. Given the observation is attack, okay, choose a basketball player. I said chosen. The probability that the basketball player chosen, given that that it is a basketball player, a true basketball player, is really, really good. But, and we can do this if we want to make this really big, right? Right? But we can make this really big if we put the threshold way down here. In other words, you give me data, it's a basketball player. You give me some more data, it's a basketball player. I don't care what you give me, it's a basketball player. Then given that it was a basketball player, the probability I chose correctly is 100%, right? I'm serious. That's true. But it turns out this is not the only thing that you want to do. You also want to make sure that the probability that you've chosen a basketball player, given that it was a jockey, you'd like this to be what? Small, right? No problem. I'll just put that right up here. So you give me data, it's a jockey. Give me some more, it's a jockey. I don't care whether it's a jockey, right? And I could do that, and I would have this always at 0%. This is the detection probability. And this is the false alarm. They're related if you've had statistics in type 1, type 2 error. You might have heard of this, a similar sort of description. In radar, it's referred to as detection and false alarm probability. And here is the situation. That you want to make this big, you want to make this small. Guess what? If you make this bigger, you make this bigger. If you make this smaller, you make this smaller. There's a trade-off, and you can't get away from it. And this is true for all detection possibilities, right? A similar sort of thing is you're sitting off the coast of Maine and you're looking for income aircraft, and you want to design a box which has a green light for everything's okay and a blinking red light for you're being attacked, right? So you have a probability of detection, a probability of false alarm. You can have a probability of detection, which means you get a correct announcement every time you're getting attacked by always leaving that red light blinking, right? Right? 100% detection. Or if you let the green light all the time, you would have 0 false alarm, right? And the point is that trade-off occurs as this threshold begins to move down this axis. This is true for the Fisher discriminant function. It's true for any classifier, any detection theory sort of problem that you have, is you have to weigh the detection probability versus the false alarm probability, and which one is more important to you? Can you live with a few alarms, few false alarms? Maybe if you're trying to detect a thermonuclear attack, yeah, you could live with a few false alarms and trading off missing a few incoming missiles, right? So it's very problem dependent on what you want to do. So we have this situation. The way that this is measured usually is through a something called a receiver operating characteristic, on our ROC curve. And again, this is for the Fisher discriminant function, but can be applied to any classifier. And it's a trade-off between the detection probability and the false alarm probability. So it's called an ROC curve. Receiver operating characteristic. Receiver operating characteristic curve. And the receiver operating characteristic curve typically looks like this. Beta versus alpha. These are probabilities, so they're bounded by 1. And the curve usually goes like this. And this tells us the trade-off between the two. Remember, we can have, let's see, is that right? Beta is equal to 0. Yeah, this is right. This is right. We can have a 0% false alarm, but we have a 0% detection rate too, right? So that's not too good. Here we have a 100% detection rate, but 100% false alarm, so that's not good either. We have to rather have a trade-off. Now, you'll notice that this curve, you can actually show that this curve for any legitimate receiver must always lie above this 45-degree line, because this 45-degree line means a coin flip. You get a data, you make a coin flip. You make half of your corrections correct, half of your decisions correct, half of them incorrect. So it's always above this. Now, how do we get this curve? How do we get this curve? We can do it actually empirically through a Fisher discriminant in the way that we perform this operation. For example, let me redraw these zeros and x's here. So this might be, for example, the result of our Fisher discriminant function. We choose a specific threshold. Let's suppose we choose the threshold right here. We can actually make an empirical estimate of our false alarm and our false alarm versus our detection probability here. What is the false alarm? That's a probability of detecting a basketball player given that it's a basketball player. Well, what's our decision? So it's a probability of getting an X when it should be an X, right? Well, the probability of X giving that it's an X, given that you said that it was an X, it means everything up here you're going to announce as an X, right? A basketball player. Everything up here. So given that it's an X means that your observation actually has occurred up here, and from this we can actually count the percentage of X's, can't we? The percentage of X's is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 X's, 11, 12, 13, 14. 11 over 14 would be our estimate of the detection probability if we were to choose our threshold at that point. Does that make sense? And you can see what happens. It's going to stay exactly that same until it goes over one of the empirical results here. As soon as it goes over a data point, it's going to change every time. But it's going to be monotonic. Now let's look at alpha. Alpha is the probability that you announced a 0 given that it's an X. No, is that right? No, probability that you announced an X given that it's a 0. That's what it is. Probability that you announced an X given that it was a 0. Well, the fact you announced it as a 0 means that the result is going to lie within here. So this part we use for beta, this part we use for alpha. And this is going to be what? The percent of X's over here. We only have 2 X's here. So it's 2 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2 twelfths. So that is the detection or the false alarm probability. Did I make a mistake? Okay. So what happens is for this value of threshold, we can actually choose a point on here. And every value of the threshold we choose is going to be different. In fact, this is actually, what do we call it? Parametric curve, where down here at this point, this is the threshold equal to minus infinity. This is the threshold equal to infinity. Those are those ridiculous decisions that we have. And as you move from minus infinity to infinity, the threshold comes this way, and then it comes down here as t goes to infinity. So the threshold determines the receiver operating characteristic curve. This is true for the Fisher discriminant function, and is true for any classifier that one uses where the final decision is made by a binary threshold, a yes or a no. Okay? Yeah.
On the left, wouldn't a false alarm be when the zero's on the right side of the line? Because you only detect the circles on the right side of the line, don't you?
Huh?
Wouldn't you detect, when you set the threshold there, don't you only detect things that are on the right side? So a false alarm.
You detect things on the left side too. But don't forget what we're doing is we're detecting basketball players. Okay? Jockeys or whatever's left. So it's the basketball players that we're detecting. Okay? So the detection probability is as follows. I announce that it's a basketball player. Given that it's a basketball player, what's the probability that I'm right? Well, given that it's a basketball player, it means that the observation came in to the right of the threshold. Right? So my probability of being right is my number of x's divided by my number of data points over here. Right? The second one, the false alarm probability, is the probability that I say it's a basketball player, but it's not a basketball player. It's a jockey.
Yeah, that's not.
Yeah.
That's what I'm saying. And wouldn't it do the circles on the right side of the threshold where you'd say I thought it was
No, given that it's a jockey. Oh, you're right.
Yeah.
Do I have it backwards? Okay, wait. Yes, your point is well made. The probability that it has to be on the left because we can't just use a dot on the right. So given that it's a 0, given that it's an x.
Is the first part
0, okay.
Let me just ask you, is the first part the probability that you are calling it an x?
Yes, the probability that you've announced of x given that it is an x. That's your detection probability.
If the denominator shouldn't be 14, it should be the number of the crosses, not just the crosses and the beta part.
The fact that you have said it's an x means it's over on this side, right? Okay. And so the probability that it's an x given that it's over here is equal to 11/14. I'm pretty sure of that. The alpha, on the other hand, is the probability that you said it was a jockey given that it was a basketball player. And that's a, I don't like that either.
Dr. Marks, I think the beta case,
Yeah.
what you want to do is you want to say, of all the x's I have, how many do I consider to be an x? So all the x's you have is 13, of which 11 are in that above the threshold. So the beta would be 11 over 13.
No, I don't know. I don't think so.
What's the number of
Let me show you a result that I have here, which I did when I was less confused in my life. Can we go ahead and zoom in on here, please? Here's a case where I hope you can see it. Here's the threshold, and here's the Fisher discriminant. So the alpha is the 1 over 5, is 1/5. That's a probability of not performing the detection correctly. And the beta is equal to 3 out of 4, which is these 3 on the right side divided by 4.
Well, but there's 4 x's as well. I mean, it's true that there are 4 things above the threshold, but there are 4 x's.
Mm-hmm.
So you detect 3 out of the 4 x's. For the alpha, you consider 1
Oh,
of
you're
the
right.
5
You're right. Okay, alpha is equal to 1 out of 5. So that means if you put your threshold here, okay, your beta is equal to 3/4, which means 3 out of the 4. Alpha is equal to 1 out of 5.
1 out of the 5 O's is above the threshold.
1 out of the 5 O's. 1 out of the 5 O's. Okay, that's correct. let me show you a less confusing probabilistic way of doing it, which is normally done on the density functions. And from this, we should be able to decipher it pretty easily, too. We normally have what we refer to in detection theory as the H-naughts hypothesis testing, where this is H-naught and this is H1. This would be the basketball players, and this would be not the basketball players. Okay? Now, in this case, what we have to do is we have to choose a threshold, and this is the actual probability density function corresponding to H-naught. This is the probability density function corresponding to H1. And if we perform this, the value of alpha well, let's do the probability of beta. Beta is equal to the probability that you've announced H-naught given that it's H-naught. Is that right? Or H1. I'm sorry, H1. I have this backwards. This is the basketball players. This is not a basketball player. So the detection probability is a probability of H1 given H1. Is that right? Which corresponds to this area under the density function. It corresponds to this density under this under the density function, which which takes that correctly. So it's equal to the percentage of the percentage, as Megan was saying, the percentage of correct results on the right of the threshold. In a similar fashion, alpha is equal to the probability that H1 occurs given that H-naught has occurred, which is equal to, in classic detection theory, equal to this result, right? It's equal to this area under the curve. So you want to make this area under the curve small, and you want to make this area under the curve large. And clearly, as you move the threshold, you increase both, or you decrease both, okay? And so this ROC curve, which I explained very poorly from the empirical result. This is the same thing for the empirical result, except we have the x's here, and you can kind of think of fitting some sort of distribution to the x's for the H1, and then we have the zeros here. We would call this the H sub 0. So it's the same idea as here. And so what happens, we set a value of a threshold. We set a value of threshold, and we have a beta and an alpha. And for this value of threshold, there's a certain alpha here, and there's a certain beta here, and we get a number, and then we move this threshold, the alpha and beta change, we get another number, and so in the end we generate this ROC curve. Okay? And what this corresponds to, again, and what I got hung up on, was that the x's here are essentially samples from this distribution, and the zeros are sampled from this distribution. In some cases, you can actually put in the model what the shape of this is, be it Gaussian or whatever. In other cases, you don't know in your a priori, so you just assume that these densities are given and characterized by the empirical data. And you can compute these areas. You can compute these areas corresponding to X and O counting. Okay? Does that muddy it up enough? Okay, any questions on that? And I would emphasize, too, that this is not only true on the Fisher discriminant classifier, but it's true on any detector where you're making a Boolean result of yes and no. You're always going to have the ROC curve relationship. So let's go over and let's see what we did today. We did preliminaries. I did not do the minimizing the Fisher distance, which was on page 6 and 7 of the handouts. I didn't do the gradient lemma. Now the gradient lemma, which is on the first page, A, B, and C, is actually used in the proof here. So that's the reason that the gradient lemma wasn't used. But we did talk about the centers of mass, the standard deviation projections, the scatter matrices, and the minimizing of the Fisher distance in the summary. Okay? That's it. Thank you for your attention.